Download this code from codegive.com, link in the description below. OK, let's dive into the world of signals in C. This tutorial will provide a comprehensive introduction to signals, covering their purpose, how they work, common signals, how to handle them, and best practices with code examples. What are signals? Signals are a form of inter-process communication, IPC, and exception handling mechanism in Unix-like operating systems. They are used to notify a process about an event that has occurred. These events can be external events, events triggered by the operating system, another process, or the user, example pressing ctrl+c. Internal events, events arising from within the process itself, example division by zero, illegal memory access. Think of signals as software interrupts. When a signal is delivered to a process, the normal flow of execution is interrupted. The process can then 1. Ignore the signal *. This is possible for some signals, but not all, especially sigkill and sigstop. 2. Catch the signal *. The process executes a special function, called a signal handler, to respond to the signal. 3. Use the default action *. The operating system has a default action for each signal, such as terminating the process, stopping it, or ignoring the signal. Why use signals? Asynchronous event handling. Signals allow a process to respond to events as they occur, without the need for constant polling. This is crucial for responsiveness and efficient use of CPU time. Error handling. Signals can be used to detect and handle exceptional conditions like division by zero, invalid memory access, or other runtime errors. Process control. Signals provide a way for users or other processes to control the execution of a running process, example stopping, resuming, or terminating it. IPC. Signals can be used as a simple form of inter-process communication, although more robust mechanisms like pipes, message queues, or shared memory are generally preferred for complex interactions. Common signals. Here's a table of some of the most frequently encountered signals and their meanings. Signal name, number, default action description. SIUP1 terminate, hang up detected on controlling terminal or death of controlling process. SIGINT2 terminate interrupt from keyboard, ctrl+c. SIGQUIT 3 core dump quit from keyboard, ctrl+\\. SIGIL 4 core dump illegal instruction. SIGTRAP 5 core dump trace / breakpoint trap. SIGABRITE 6 core dump abort signal from abort. SIGBUS 7 core dump bus error, bad memory access. SIF8 core dump floating point exception. SIGKILL 9 terminate kill signal, cannot be caught or ignored. SIGUSR 110 terminate user defines signal 1. SIGSEGV 11 core dump invalid memory reference, segmentation fault. SIGUSR 212 terminate user defines signal 2. SIGPIPE 13 terminate write to pipe with no readers. SIGALREAM 14 terminate timer signal from alarm. SIGTERM 15 terminate termination signal. SIGSTKFloat 16 terminate stack fault on coprocessor stack. SIGCLD 17 ignore child stopped or terminated. SIGCONT 18 continue if stopped. SIGSTOP 19 stop signal, cannot be caught or ignored. SIGSTP20 stop typed at terminal, ctrl+z. SIGTIN 21 stop background process attempting read from TTY. SIGTO 22 stop background process attempting write to TTY. SIGURG 23 ignore urgent condition on socket. SIGSPU 24 terminate CPU time limit exceeded. SIGSPS 25 terminate file size limit exceeded. SIGTALREAM 26 terminate virtual alarm clock. SIGPROF 27 terminate profiling timer expired. SIGWinch 28 ignore window size change. SIGO 29 terminate IO now possible. SIGPR 30 terminate power failure. SIGSIT 31 core dump bad system call. Asterisk note asterisk signal numbers can vary slightly between operating systems. It's best to use the symbolic signal names, example SIGINT, rather than their numerical values for portability. Handling signals in C. The primary function for handling signals in C is signal. There's also a more robust function called SIGAction, which we'll discuss later. Explanation asterisk. 1 includes signal.h asterisk includes the necessary header file for signal handling functions and definitions. 2 void SIGINT_handler, int signo, asterisk this is the signal handler function. It takes an integer argument signo, which represents the signal number that triggered the handler. The handler should be declared with a void return type. 3 signal, SIGINT, SIGINT_handler, asterisk this is the core function. It registers the SIGINT_handler function to be called when the SIGINT signal is received. Asterisk signal, takes 2 arguments. Asterisk the first argument is the signal you want to handle, example SIGINT. Asterisk the second argument is a pointer to the signal handler function. You can also use sig_ign to ignore the signal or sig_dfl to restore the default action. Asterisk the signal, function returns sig_error on error, which you should always check. 4 per signal, asterisk if signal, fails, per prints an error message to str. 5 exit, 0, asterisk inside the signal handler, you can perform cleanup operations, example closing files, freeing memory, before exiting the program. The exit function terminates the program. 6 while, 1, asterisk this creates an infinite loop to simulate a program that is continuously running. 7 sleep, 1, asterisk this function pauses the program's execution for 1 second. This is just for demonstration purposes so you can see the output before you press ctrl+c. How to compile and run asterisk. 1 save the code as a .c file, example signal_example.c. 2 compile using a C compiler, example GCC. 3 run the executable. 4 press ctrl+c in the terminal. You should see the message received SIGINT, ctrl+c. Exiting gracefully and the program will terminate. SIGAction, a more robust alternative. The signal function has some limitations, example it's not portable across all Unix systems, and its behavior can be unpredictable in multi-threaded programs. The SIGAction function is a more modern and portable alternative. Explanation of SIGAction, asterisk. 1 struct SIGAction SA, asterisk declares a SIGAction structure. This structure contains information about the signal handling behavior. 2 SA.SA_handler equals SIGINT_handler, asterisk sets the signal handler function to SIGINT_handler. This is the same as with signal. 3 SIGEMPTOSET, and SA.SA_mask, asterisk initializes the signal mask, SA.SA_mask, to be empty. The signal mask specifies which signals should be blocked, prevented from being delivered, while the signal handler is executing. An empty mask means no signals are blocked. This is generally a good default to avoid reentrancy issues. You can use SIGADSET and SIGDELSET to add or remove signals from the mask. 4 SA.SA_flags equals 0, asterisk sets the flags, SA.SA_flags, to 0. These flags control various aspects of signal handling. Common flags include SA_restart, which automatically restarts system calls interrupted by the signal, and SA_SIGINFO, which allows the signal handler to receive more information about the signal. 5. SIGAction, SIGINT, and SA, null, asterisk registers the signal handler using SIGAction. Asterisk the first argument is the signal to handle, example SIGINT. Asterisk the second argument is a pointer to the SIGAction structure. Asterisk the third argument is null. If you want to retrieve the previous signal action for SIGINT, you could pass a pointer to another SIGAction structure here. Important considerations and best practices. Asterisk reentrancy asterisk signal handlers should be reentrant. This means they should be safe to call at any time, even if the program is already in the middle of executing another function. Avoid using non-reentrant functions, example printf, malloc, inside signal handlers. If you must use printf for debugging, consider using write to standard output instead, as write is generally considered reentrant. Use atomic operations, example incrementing or decrementing a volatile integer, to modify shared variables. Asterisk volatile keyword asterisk when accessing shared variables, variables that are both modified inside the signal handler and accessed in the main program, declare them as volatile. This tells the compiler that the variable's value can change at any time, example due to a signal, so the compiler shouldn't optimize access to it. Asterisk signal masking asterisk carefully consider the signals you block using SA.SA_mask. Blocking the wrong signals can lead to deadlocks or other unexpected behavior. Asterisk asynchronous signal safe functions asterisk use asynchronous signal safe functions in signal handlers. These functions are guaranteed to be safe to call from within a signal handler. The Man7 signal page lists which functions are async signal safe. Examples include *_exit, *write, *sigempty_set, sigfill_set, sigadd_set, sigdel_set, *thread_kill. *Avoid complex logic in handlers *keep your signal handlers as short and simple as possible. Ideally, they should only set a flag or perform a very small amount of work and return. Defer more complex processing to the main program loop. Race conditions be aware of potential race conditions when using signals for inter-process communication or synchronization. Signals are asynchronous, so there's no guarantee about the order in which they will be delivered relative to other events in the program. Consider using synchronization primitives, example mutexes, semaphores, to avoid race conditions. Avoid catching sigkill and sigstop you cannot catch or ignore the sigkill, kill, and sigstop, stop, signals. These signals are designed to provide a guaranteed way to terminate or stop a process, regardless of its internal state. Example, using volatile and a flag. This example demonstrates the use of volatile to safely update a shared variable from a signal handler. In this example, the stop_flag variable is declared as volatile sig_atomic_t. Sig_atomic_t is an integer type that can be modified as one atomic operation, preventing any corruption that may occur due to partial writes. The signal handler simply sets the stop_flag to 1 when SIGINT is received. The main loop checks the stop_flag and exits when it becomes 1. Example, sending signals to other processes. You can use the kill function to send signals to other processes. You need to know the process ID, PID, of the target process. This example shows how to send a sigusr1 signal to another process. How to use *. 1. Compile the code, gcc kill_example.co kill_example. 2. Run the program, providing the PID of the target process as a command line argument, /kill_example 12345, replace 12345 with the actual PID. Important security considerations **** You can only send signals to processes that you own, i.e., processes that you have the same user ID as, or to processes that have the same group ID as you, or if you have root privileges. This is a security measure to prevent unauthorized users from interfering with other processes. Be careful when sending signals to arbitrary PIDs. You could accidentally terminate or disrupt a critical system process. In summary, signals are a powerful but potentially complex mechanism in C. By understanding how signals work, how to handle them safely, and the importance of reentrancy and volatile, you can effectively use signals to build more robust and responsive applications. Remember to always check for errors when calling signal-related functions and to follow best practices to avoid unexpected behavior. For more advanced use cases, explore features like signal sets, real-time signals, and the siginfo_t structure, for getting more information about the signal.